Today we will study about the flow through the orifice, how liquid flow through the orifice and what are the types of orifice that we will discuss now. Now we go through the definition of orifice. What is orifice? Orifice is a small opening on the side or at the bottom of the tank of any cross section. That may be circular, rectangular or any other shape. So write the definition which I said now. Orifice is a small opening at the side or bottom of the tank of any cross section such as circular, rectangular and used for flow of the liquid. Here we go through the types of orifice. What are the types of orifice? Let's discuss now. There are different types of orifice on the different basis, on the basis of shape and on the basis of head of orifice and on the basis of discharging nature. On the basis of discharging nature, and we have different types of orifice. First of all, on the basis of size. On the basis of size of orifice, there is small orifice and large orifice. What is small orifice? What is large orifice? We will discuss now. Suppose we have tank fitted with orifice at its side. Let x is the depth of the orifice and h is the height of the water level from center of the orifice. If head of the center of the orifice is less than this 5 times of this x, then it is called large orifice. If head from the center of the orifice is greater than 5 times the depth of the orifice, then it is called small orifice. It depends upon this height and the depth of the orifice. We will write the definition using this concept. If the head of the liquid from center of the orifice is more than the 5 times the depth of the orifice, then it is called small orifice. This is the definition of small orifice, and we write the definition of large orifice. Here we write in small place of small we write large. Here also small we write large, and we have to make changes. This is less than. If the head of the liquid from center of the orifice is less than 5 times the depth of the orifice, then such types of orifice called large types of orifice. If head is more than 5 times of the depth, it is called small orifice. And if head of the liquid from center of the orifice is less than 5 times, then it is called large orifice. So this is on the basis of size of the orifice. Now we go to other basis. And we have another basis. On the basis of area of cross section, we have different type of orifice. We have circular orifice, rectangular orifice, and other triangular orifice. Generally, circular orifice is used in practice in all the vessels that we can see in our daily life. By the name, we know this is the circular types of orifice. This types of orifice, circular. Triangular orifice, this is of triangle shape. Rectangular orifice, this is rectangle shape. This is on the basis of cross sectional area, on the basis of geometry of. On the basis of nature of discharge, we have two types of orifice. First one is free discharging orifice, and second is drawn or submerged orifice. Drawn or submerged orifice is of two types. First is fully submerged orifice, and second is partially submerged. We will do the derivation of different types of orifice. This small orifice, large orifice, and this fully submerged orifice and partial submerged orifice. We will do the derivation of these types of four types of orifice. Now we will study about small orifice in detail, and we will do its derivation. In next video we will discuss and do the derivation on a large orifice, and then after we will do about this fully submerged orifice and partially submerged orifice. Here we go with the flow through small orifice. First of all, we will make a simple figure here for a small orifice. Suppose this is the tank. This is orifice here. If liquid is here, free surface is here, liquid free surface here, and if orifice is open, the liquid get discharged here. This is the center of the orifice. This is, we suppose, H. And we suppose here 0.1. And when liquid flows from the tank to the outside, At any section, the liquid Z form a area of minimum cross section. This area of minimum cross section is called vena contracta. This is vena contracta. Vena contracta is the section in which the flowing liquid have a area of minimum cross section. Suppose let the area of this orifice is small a and the area of this vena contracta is AC, then AC is always less than A. Area of vena contracta is less than the area of the orifice. Suppose we let the area of cross section as tank as A. So we write the consideration here. We consider a tank fitted with a circular orifice here in its side, and we write this H. This H is head of liquid from center of the orifice. We consider point 1 here, and we consider this point area of vena contracta point 2 at same level. Here this is point 1 and this is in level with this point 2. These are on the same level. Point 1 is inside the tank, whereas point 2 is at vena contracta. And we can apply Bernoulli's equation between this section and this section, section 1 and 2. This H is the constant head. At point 1 we have lead pressure P1, then pressure head P1 upon rho g plus here velocity is V1 and velocity at V is square upon 2g plus let this is at height z point 1 and point 2 are on same level, both have height z, z1 equal to P2 upon rho g plus V2 square upon 2g plus z2, z1 equal to z2 equals to z. So we have remaining, and P2 is on the atmosphere, so this is 0. V1, when the liquid discharges from here, the velocity at this point remains same, so this V1 is 0 and this is 0, so we have only this P1 and we have P1 upon rho g equal to V2 square upon 2g, but P1 upon rho g is the head from the free surface to this point, so we can write P1 upon rho g is equal to H. So we have H equal to V2 square upon 2g and V2 equal to root under 2gh. This is the velocity of a flowing fluid at this point B2 vena contracta, and this is the theoretical value. Theoretical value of velocity. We can get actual value by multiplying with coefficient of velocity. Therefore V2, this is actual. Actual velocity is CV root under 2GH. This is the value of actual velocity at point 2. This V2 actual. V2 is always greater than V2 actual, because in actual velocity there are some losses. V2 actual is always less than V2. So we write what are the causes of this V2 actually is always less than V2. We write here. So this is the derivation of this small orifice. Finish. Now we write the what are the points that create V2 actually is always less than V2. We have derived V2 actual velocity. V2 is CV root under 2GH. This is the velocity through vena contracta velocity, and we have to find the rate of flow through the small orifice. That is, we have Q equal to area of vena contracta AC into this V2. If this is area of orifice, let this is A0, and AC is the area of vena contracta, then we have CC is equal to this area of vena contracta upon area of orifice. This CC is less than 1, should be less than 1. Area of vena contracta is less than area of orifice. So we can place here AC equal to A0 into CC into V2. This A0 is the area of orifice into CC into V2. This is the rate of flow through the small orifice. This is actual value of flow through the orifice, and losses are due to the viscosity of the liquid. And next we have the surface tension of the liquid. And we have other due to air resistance. These are the losses. In place of V2 we can write here Q equal to CC into A0 into this value of V2. We substitute here. Therefore value of Q become CC CB into A0 into root under 2GH, and we can substitute this value of CC into CB. Coefficient of contraction into coefficient of velocity is coefficient of discharge. We get the theoretical discharge, and if we put CD, we get the actual discharge through the small orifice. In the next video we will continue to our topic of large orifice.